In this tutorial, we will look at how to use stoichiometry tables to solve advanced stoichiometry problems in which we need to determine the composition of the system at a given point in time. This type of analysis is useful for studying reaction kinetics in equilibrium systems. In your first semester general chemistry course, you practiced calculations involving stoichiometry. You were able to calculate the amounts of reactants and products produced in chemical reactions, including limiting reactant situations. In these calculations, we usually assume that the reaction went to completion. In Chem 51, we will apply these concepts of stoichiometry to situations in which we want to maybe follow the progress of the reaction as it proceeds, which is the study of kinetics, not just what it looks like at the end, or determine the amount of reactants and products for reactions that don't go to completion, but rather reach an equilibrium state. The main ideas are the same. The balanced chemical equation gives the recipe for the reaction in terms of moles. The mole ratios in the balanced chemical equation tell us the relative amounts of each reactant and product that react or are produced. Moles of any reactant or product can be converted to or from grams using the molar mass, molarity or volume if it's a solution by using the formula for molarity. Molarity is moles over volume. Or to volume or pressure if it's a gas using the ideal gas law, PV equals nRT. However, in order to accommodate the new questions we'll be asking, we have to be a bit more organized in how we approach the advanced problems. The following tutorial will help you organize the information needed for these more advanced problems. A good way to organize the information for a stoichiometry problem is to set up a table using the balanced chemical equation as the first row and moles of each species below that. We typically include rows for initial conditions, change, and new or final. For example, if the reaction that we're considering is the reaction between carbon monoxide gas and hydrogen gas to form methanol, we would create a table like the following. The first row of the table is the chemical reaction with the respective coefficients. We have a row for the initial moles of reactants and products, a row for change, and a row for the new moles, both expression and numerical value. Now we can fill in what we know and use variables and expressions for the quantities that we don't yet know. For example, if you were told that you started with 7 moles of carbon monoxide gas and 10 moles of hydrogen gas, you can add these quantities to the table. If no information is given about a particular reactant or product, we generally assume that it starts at 0. So as we see in the table below, we've put 7 below the carbon monoxide, 10 below hydrogen, and 0 below the methanol. Note that if the amounts in the problem are given in grams or molarity, you would want to convert to moles first because our table has a row for the initial moles. The change row indicates how much of each reactant is converted to products. When following the progress of a reaction, we generally don't know these amounts in terms of actual moles, but we do know the relative changes at any given time. According to the balanced chemical equation, for every mole of carbon monoxide gas that is lost, 2 moles of hydrogen gas are lost, and 1 mole of methanol gas are produced. We use x's to show the relative changes as in the table below. Note that negative signs are used for the change in moles of the reactants to show the loss of these species. Positive signs are used for the products to show the production of these species. The coefficients in the balanced chemical equation become the coefficients in front of the x values. Combining the information in the first 2 rows gives the following. This general setup is very useful for calculating the amounts of reactants and/or products at any given moment in a reaction. The numerical value for the new moles depends on what the value of x is. What you do next depends on the rest of the information given in the problem and what you're asked to calculate. Let's look at 2 specific examples using this initial setup. In the first example, we'll look at a reaction that involves a limiting reactant, but the reaction goes to completion. We'll look at the reaction again of the carbon monoxide gas reacting with hydrogen gas to form methanol. The question is, how many moles of methanol are produced from 7 moles of carbon monoxide gas and 10 moles of hydrogen gas? If the reaction goes to completion, then the new or final amount of the limiting reactant will be 0, but there will still be some of the non-limiting reactant left. So how do we tell which reactant is limiting? One way to find out is to determine the value of X that gives a 0 result for one of the reactants and a positive result for the other reactant. There are 2 possibilities for X that would give 0 final moles. Let's look at those 2 possible solutions. Let's first assume that carbon monoxide is the limiting reactant. If that's the case, then its concentration or its amount should go to 0. Using 7 minus X as the expression for carbon monoxide, if 7 minus X equals 0, that would make the value of X equal to 7. However, if we use the value of X equals 7 and we plug that into the expression for hydrogen, we get 10 minus 2 times 7 is negative 4, which is an impossible amount for the amount of hydrogen that would be left over at the end of the reaction. So that means that carbon monoxide cannot be our limiting reactant. Let's next try to see if hydrogen is our limiting reactant. Its expression is 10 minus 2x. If we set that equal to 0, then x would be equal to 5. If we use x is equal to 5, the final moles of hydrogen would be 0. The final moles of carbon monoxide would be 7 minus x, or 7 minus 5, is equal to 2. That's a positive number and the correct solution. Therefore, hydrogen must be our limiting reactant, x will be equal to 5, and we can plug in that value of x into the other expressions to get a value of 2 for the carbon monoxide gas and 5 for the methanol. Let's look at a second example. This one is involving reactants and products prior to completion of the reaction. We'll stay with the same reaction of carbon monoxide gas with hydrogen gas forming methanol. And we'll stay with the same initial conditions of 7 moles of carbon monoxide and 10 moles of hydrogen. But this time we'll ask the question, how many moles of each reactant or product are present when 2 moles of methanol have been produced? In this problem, we're given the initial moles of carbon monoxide and hydrogen gas, as well as the new moles of the methanol gas. So starting with our table as we have before, we can already plug in the value for the methanol gas that's formed. That was the number 2 given in the problem. Since the value of methanol is equal to x, we already have the value of x in this situation. Substituting x is equal to 2 into the expressions for carbon monoxide gas and hydrogen gas, give 5 for carbon monoxide gas and 6 moles of the hydrogen gas. The previous 2 examples walked you through setting up more advanced stoichiometry problems using moles only. Of course, real problems will most likely involve grams or molarities, so you may have to convert the given information to moles prior to constructing your table, and/or convert your new moles to grams or molarity after solving the table. The conversion between grams and moles is accomplished using the molar mass. To convert between molarity and moles, use the equation molarity equals moles over volume. If your problem involves gases and you need to convert between moles and either pressure or volume, use the ideal gas law, PV equals nRT. Try the following sample problems to see if you can apply this technique to solve for the requested information. Here's the first sample problem. Remember, we want to set up stoichiometry tables to help solve these problems. Click to pause the video as you try to solve this problem. The answer will be shown on the next slide. If you were not able to get the answer shown, go back and review the stoichiometry table setup. A partially filled table is also posted in Canvas if you need a hint. If you're still struggling, please email Professor Troutman, or better yet, stop by her office hours. Here's a second sample problem. Again, pause the video to solve the problem. The answer is shown on the next slide. In this tutorial, we've looked at how to set up stoichiometry tables. These tables will be used extensively in Chem 51 to look at reaction kinetics and equilibrium.